Hey friends, my name is Osama. If you're new to my channel is all about nuclear science and technology. I have a background in nuclear engineering and I love to talk about all things related to nuclear. Now imagine nuclear reactors cooled by liquid molten salt. Now that sounds like science fiction because nuclear reactors have always been cooled by liquid water. In this video, I'll be covering molten salt reactors, which is a generation 4 reactor design. Also in this video, I'll be going through the history of molten salt reactors, or simply known as MSRs, how these reactors were revived. Why are countries across the world racing ahead to develop this technology? I'll answer that. Also, I'll cover different types of MSRs, right? So there's not only one type, there's many different types. Also, reactor specifications, how exactly this reactor works. Reactor safety, is this reactor safe? And also molten salt reactor types located across the world. So let's jump into the history of molten salt reactors. It all starts in the year 1960 when the United States developed its own MSR concept in the Oak Ridge National Labs. So originally this concept was based on the aircraft reactor experiment. Originally, the experiment was designed to understand the feasibility of a nuclear reactor for propulsion of a supersonic aircraft. Now, these aircrafts would be able to fly across the world without refueling for several months. Okay, so liquid thorium was considered as well as uranium as fuels for this reactor. Now, there are some technical considerations when designing a reactor that could fit inside an aircraft. Well, there's number one, there's weight. Uranium is very, very heavy. Okay, and you need lightweight for an aircraft to fly for long periods of time. There's also other considerations, but overall, eventually a small prototype reactor was built in Oak Ridge, which was an 8 megawatt experimental molten salt reactor, and it operated until in Oak Ridge till the year 1969. Overall, this prototype was used to test fuels like U-235 and also U-233. It eventually led to the development and building of an MSR breeder, which uses thorium and also would eventually operate in a low thermal neutron spectrum. Overall, this reactor logged a total of 10,000 operating hours. Why is this important? The reason why is because molten salt reactors are a proven concept. It's been in an experimental phase. Eventually, there was lack of interest from the government in the United States, but now there is a steady revival of this technology. Countries across the world are racing against the clock to develop this technology, and I'll explain why. So let's talk about the revival of the MSR. In the last decade, there has been a renewed interest in MSR technology. It's only one of 6 generation 4 reactor designs which has been selected for further development. So countries like Japan, Russia, China, France, United States, and Canada are investigating this reactor and starting to develop this technology. Now, the Generation 4 International Forum has placed the initial focus of molten salt reactors on the burner reactor rather than the breeder reactor. So the molten salt reactor can be used as a burner reactor, which actually is used to burn conventional spent fuel from modern day reactors like light water reactors and also CANDU reactors, rather than breeder reactors. And breeder reactors are reactors that are used to breed more fuel that can be used for the reactor itself or for other conventional reactor designs. The reason why is because breeder reactors come with a little bit more of a proliferation risk. Burner reactors, on the other hand, are used to reduce the inventory of spent nuclear waste, which is incredible for the world. Imagine using spent nuclear fuel to power future reactor types. It's incredible. You have a closed loop cycle. And since 2005, R&D has primarily been focused toward developing these types of reactors. Burner reactors, which use a fast neutron spectrum. However, throughout the years, significant changes in design philosophy has been seen and embraced by other countries. This has led to designing simpler, less ambitious molten salt reactors that don't necessarily breed new fuel, and they don't require online fuel reprocessing, and also has a well-established built uranium fuel cycle. So overall, this design philosophy will help take this molten salt reactor technology and start commercializing it. Right, so let's talk about the different types of MSRs. Now, overall, there are 2 different categories of molten salt reactor designs. Okay, and I'll start off with the first one. The first one is a homogeneous design. Okay, so in terms of MSRs, the homogeneous design uses molten liquid fluoride salt coolant. Okay, so this is the coolant that's running throughout the reactor, but also uses a liquid fuel that's mixed together. So imagine you have a fish tank and you can simply add the fuel. You can add the food, okay, to it, and the the fuel and the coolant are mixed together in one entity. This is really, really unique concept, okay? So thorium, uranium, plutonium can be processed into liquid fluoride salts that are readily dissolved into these lithium fluoride or lithium beryllium fluoride salt. Fuel life within this reactor is around 4 to 7 years. All right, so that's how long the fuel spends within this reactor until it needs to be refueled. Now, the second type is a heterogeneous design. Okay, and it's called heterogeneous because it's both liquid and solids. The coolant is a molten fluoride salt, but the fuel itself are solid fuels. So molten salt reactors, they use solid fuels in ceramic fuels, just like conventional reactors, but the design of these fuels can be very different. So you'll see unique designs like prisms, plates, pebbles, or even designs that have liquid fuel in static tubes. So it's very interesting. There's a lot of innovative technology going out in this realm. If there were to be a commercial nuclear reactor produced and put on the market, most likely it would be this one, because this is just the focus of many countries across the world. So there you have it. Those are the two types of fuel designs that MSRs are generally categorized under: the homogeneous and the heterogeneous. Right, so let's talk a little bit more about the reactor technical specifications and go into the weeds of what this reactor is all about. Now, while operating, these salts remain in a non-pressurized liquid form that range from around 500 degrees and can also go up to 1,400 degrees Celsius, right? So this is very different from conventional nuclear reactors that generally operate at around 300 degrees Celsius. You're seeing that these MSRs are operating at very, very high temperatures. And this is actually a really great benefit. The reason why it's an incredible advantage is because these reactors can be deployed for two means. One is electricity production, but also they can be used for supplying process heat for industries like mining and other industries. And you could even optimize reactors which are being deployed for both purposes. Also, the primary loop in these reactors is the coolant, okay? And this transfers heat to the secondary salt circuit, and then this is used to create steam or process heat, okay? So this is kind of the arrangement that some of these reactors have. Now, molten salt reactors, especially molten salt fast reactors, have a negative temperature and void reactivity coefficient. Okay, what does that mean? Basically, this means that they are ultra safe. Doesn't mean that conventional nuclear reactors aren't ultra safe. They are very, very safe as well, but it just means that these molten salt reactors have some really unique safety features which are not there in conventional nuclear reactors. Overall, this is a selling point for MSRs. Another interesting feature that MSRs have is that they have overall lower fissile inventory. Lower fissile inventory, why is this important? Basically, this has a lower proliferation concern, all right? And it also has benefits of low cost of refueling. Like I said, some of these reactors are being refueled after 4 or 7 years. Conventional nuclear reactors are refueled every single year, around once per year, but these reactors need to be refueled after 4 to 7 years. Overall, these reactors also have a very high burnup. What is burnup? Basically, it's how much energy can be extracted from a fuel source. High burnup values are a lot better since it means that the reactor is more efficiently using the fuel source. So, however, reprocessing these fuel salts is far from commercialization. Reprocessing these fuel salts online is another technical obstacle which a lot of research and development is currently going on. Online reprocessing is basically while the reactor is operating, these fuel salts are removed from the system and they are reprocessed. Why would you need online refueling? Why can't you let the fuel just swim around in these reactors? Well, the benefit of reprocessing or removing fission products while the reactor is operating comes with the benefit of allowing the fuel to reach higher burnup targets. So this is anticipated to be around greater than 50% burnup, which is incredible for nuclear reactors. Another benefit of removing fission products is you have less decay heat being produced after the reactor shut down. And obviously this comes with its own safety benefits. Now, as fission products are removed from the reactor, they are slowly replaced with either uranium or plutonium. Other actinides or other fertile thorium or U-238 can also be placed within the fuel. So this is the type of process that's used while operating this reactor. Overall, the greater benefit of this reactor is the fact that high-level waste that's produced in this reactor, which is the fuel, only consists of the fission products, which are very short-lived radionuclides. So you'll see that the waste products that are produced from this reactor fuel and the molten salts are very short-lived. They're not necessarily gonna last as long as spent fuel from conventional nuclear reactors, which is a benefit because when it comes to waste management, you don't necessarily have to manage this waste for a very, very, very long time. Rather, these waste sources are only going to have to be managed for a couple hundred years at best. So I know I talked a lot about safety and safety systems in this reactor. Now let me talk about additional safety features that molten salt reactors have. So molten salt reactors have passive cooling systems, which is an amazing safety feature. What is passive cooling? Passive cooling is the complete opposite of active safety systems. So an active system is basically large pumps that the reactor is dependent on. If those pumps fail, then the reactor can get into trouble. But now these reactors, if these pumps do fail, it has passive safety, which uses gravity or other methods to control the reaction and safely shut down. Several other reactor designs have freeze plugs. So what is a freeze plug? In case temperatures go beyond design limits, what happens is the salt solution is drained away from the moderator, all right? So, and it's also placed inside dump tanks, which are designed specifically to prevent criticality from taking place. So this is in case the reactor is in a tough spot. What you could do is you could divert the salt solutions away from where the reaction is taking place, and you can safely place them inside these dump tanks, which is a very, very unique feature. Also, molten salt reactors, they are designed to shut down if expansion takes place in the fuel salts. So as if the fuel salts go beyond design limits in terms of temperature. So if they're getting way, way, way too hot, what takes place is these fuel salts expand to a level in which these molten salt reactors immediately shut down. So they have this additional safety feature. What's interesting is studies have been done and taking place where if an unintended control rod is also removed, so say there's an operator error, he or she makes a mistake, pulls out a control rod, the negative void and temperature coefficient works to passively reduce the rate of power. Because of the reactor physics within this design, the negative void and temperature coefficient can help make up for an unintended control rod that's pulled out. So overall, this reactor technology is very, very unique and has some really unique safety systems in place. Lastly, I'd like to talk about MSRs across the world. So you'll see MSRs in Russia. So Russia is developing molten salt reactors used to burn away transuranic waste from MOX fuel, okay, and other fuel sources. You'll see China also has current plans to use MSRs as an energy solutions for the northwest half of the country, because the northwest half of the country has very little access to water, and molten salt reactors come with the benefit of not using large amounts of water for cooling these reactors. So for countries across the world that have water scarcity, they don't have large rivers, they don't have large oceans or lakes which they can use for cooling these reactors. This is a phenomenal technology. Also, Oak Ridge has also revived its MSR, okay? So they were the originators of the MSR. Now they've revived this technology and they have pursued the technological development of MSRs with companies like Kairos Power. And lastly, Canada. Canada is looking into some interesting molten salt reactor designs which use spent fuel waste from CANDU reactors, seeing if they can be processed into these molten salt reactors. So overall, love the concept of MSRs and also Generation 4 reactor designs. I really found it interesting just doing a little bit of research into these reactors and also just packaging it into this video. Hope you enjoyed this video as well, and I really look forward to hearing your thoughts and comments in the comments below. Hope you get the chance to subscribe. Click the subscribe button, like, and enjoy this video. Till then, take care. Bye.